Welcome, good afternoon. Thanks for coming. I'm very pleased to introduce to you my colleague and old friend in the sense of, well, it's been
both ways.
It's been, we go back 30 years, 31 years since we first met. Alvaro is a professor of epidemiology at Hopkins Bloomberg School of Public Health with a joint appointment by Statistics and Environmental Health Sciences. Prior to Hopkins, he was associate biostatistician at the Department of Medicine in Brigham and Women's Hospital in Boston. He graduated in mathematics at the Universidad Nacional de Colombia in the beautiful city of Medellin, and went on to do training in statistics. So at Stanford with a master's and Ph.D. He has been involved in multiple studies, has led and been involved in coordinating centers for landmark studies such as the MITI Center AIDS cohort study, the MAX, since it's almost its inception in the mid-80s, the ALIVE study, more recently chronic diseases as well, more recently the kidney children, how is it called? The kidney in children diseases. What's the acronym for that study?
CKID.
More than 300 publications, if you count books, chapters, books, and journal articles. Received multiple awards, many to relate here. It would take me too long, but it includes just a couple of highlights. He's an honorary professor in his alma mater, Universidad Nacional de Colombia, an associate member, as elected member of the Colombian National Academy of Medicine, and has been chair of the statistics section of the American Statistical Association. Consultant and an advisor for multiple national and international organizations all over the world. He's been a world leader in the development and application to epidemiology in particular of statistical methods for longitudinal analysis, many of them quite novel. He's been an innovator and methodologist in finding ways to be more creative in applying methods such as repeated measures of in the context of biomarkers in HIV progression, for example, how to combine prevalence and incidence data to estimate seroconversion, parametric models in pseudoanalysis analysis, and very novel methods to analyze case cohort data using late entries. So very involved in that. He's an extraordinarily accomplished teacher, as you will see right now in the next hour. He has had we used to call him maestro in Hopkins. They still call you that. He has received 6, maybe more, 6 teaching awards at Johns Hopkins, and he's going to talk today about the pitfalls of the proportionality assumption in the context of the competing risk setting. I just hope that you're not going to tell us that we have been teaching something completely wrong all these years. Thanks, Alvaro.
Thank you very much, Javier. It's a pleasure to be here, and great institution, amazing campus. You're lucky. Enjoy it. Work hard, and go to the mountains, but not too often. Okay, so this is a topic on sort of the pitfalls and how treacherous it is in the competing risk setting to blindly assume proportionality that we always do, and this is saying, hey, maybe one should be careful in making that assumption, and don't do it. You will see why it is an issue. So competing risk is simply when the event can be of 2 types or more. That is not one event. It's not death, but it's cause of death. It's not renal replacement therapy in general, but what type of renal replacement therapy do you get? the epidemiology of the epidemiological aims is that perhaps the things that affect one are not the same that affect the other. So the heterogeneity of how risk factors may predict specific outcomes. So that's where the aim is in terms of the scientific issues. So it's not simply to divide it, but to gain more knowledge about how different events may be related to exposures. And this is a diagram of how income relates to what type of event you may receive in the first place. So this is the cumulative incidence of end-stage renal disease, which is either dialysis or my GFR, my kidneys filtrating very, very little. And that is transplant. And the cumulative incidence of transplant is this complement. Okay? So if I were to do not this funnel, but to put this in the same scale, then this red curve will be like that. Okay? But to use this, to not crowd it here, this is the way to represent this cumulative incidence, both towards the event. And you could see that this diagram indicates that for people with lower income, the ESRD accumulates higher than the people that have a better income. Okay, so that the overall proportion of people that ESRD is first is higher than that. And this distance is the timing of when that happens. Okay, so it's how frequent each one of it is, and when does that occur. And so that is the picture. And this is the notation of the cumulative incidences. So I sub 1 is the accumulation of ESRD in this group. And then this function is the complement of the cumulative incidence of transplant in that group. And this star is for the exposed. This is the exposed group, this is the unexposed. And what we want to summarize, when we went to summarize is how this modified this mixture okay? So one thing that we all do in terms of hazard is to go into this cumulative incidence and psychoanalyze it and extract from it the hazard that reproduces this cumulative incidence. Okay? And go and do the same thing here. Go to this cumulative incidence and say, who is your hazard? Who's your partner? Who is that function that if accumulated, I reproduce you? Okay? And that is one measure that is used in competing risk. And that is called the subhazards of the cumulative incidence. And you could see that this is the cumulative incidence of SRD, and this function is that this lambda 1 is the subhazard of this event in that group. And if I accumulate it, and I do a little bit of algebra, I reproduce you. Okay? And there is this one will have a lambda 1 star. And the summary measure is what is that the ratio of the lambda 1 star to lambda 1. And over here, same thing. What is the ratio of lambda 2 star to lambda 2? That is the two subhazards of transplant in the two groups. Okay? And this also is referred as the fine and gray method. Because fine and gray, in a landmark paper in 1999, were the ones who proposed this measure, this summary measure, to compare things. Okay? So that is what the subhazard is that function whose accumulation reproduces the cumulative incidences. Now, mathematically, this is the how you find that subhazard, which is nothing that how fast this cumulative incidence is increasing, the rate of change of the cumulative incidence, divided by the complement of that cumulative incidence. Okay? And that is, in parallel, the subhazard of event 2. And indeed, it can be simply shown that if I accumulate this, I will reproduce this, taking the anti-logs and blah, blah, blah. Okay? Huh? And graphically, this is what does. This is the cumulative incidence in this group. Then I go and say, how fast, the numerator of this thing is how fast are you increasing, and the denominator is this distance. Is 1 minus this complement, 1 minus it. Okay? So that's what a subhazard is. As you can see, the subhazard, the interpretation of this is that the rate of change is how many people are failing of that type now. How many people are in this instant, how many people are failing that. And the denominator is everybody that has not had that event. But that includes these who are free of both, plus the ones that have had the other event. Okay? In the denominator, this denominator are the people who are free of both at a given time, plus those that have had the other event. Okay? Then, alternatively, people have proposed another measure, which is called cause-specific hazard functions. And all it is the same numerators are these. They have the same numerators, but the denominator, you exclude not only those that have had that event, but also the ones that have had the other event. So this one is a much more affable measure, because it's among the people that are free today, what percent will develop the event in the next instant of a given type. Okay? Now, this is the oh, Santa Barbara. Okay. Sorry. Okay. So this is a more popular measure. Easier to swallow, and essentially that. As you can see, I'm using here a little bit of Martha Stewart colors. Influence because blue is 1, red is 2, and this one is purple because it has blue and red. Okay, has blue and red. So it's not and that is important because that itself that already says that it is not as specific as its name implies. Okay? And you will see a little bit of that. But even in the definition, you could see that it's not that specific. These ones are more specific. They are blue and red. but not a mixture. Now, it is always the case that this entity is greater than that, because the denominator is lower. You subtract more. Okay? And this fact that this thing is greater than that inequality between these two, unfortunately, implies or results in the fact that if you describe a process, if you describe an exposure in terms of how affects this thing, rather, if you use these entities describing how an exposure modifies these two entities, you cannot directly translate those into how the cumulative instances are transformed, because they are not linked directly to the cumulative instances. And that's the primary drawback of using this measure as the summary. Now, and graphically, the denominator of the cause specific is just that, instead of the whole thing. Now, there are three primary methods to analyze computing risk, as you will know. First of all, using cause specific hazards. And the attraction of these is that the hazard of the composite event, renal replacement therapy, is the sum of the cause-specific hazard of ASRD plus the cause-specific hazard of transplant. So it sort of divides the hazard of the composite event in the sum of the two. That is nice, sort of partitions the hazard into the sum of the two. That's another attraction of this cause-specific hazard. This method too, the finite gray, it doesn't, the partition that it does is of the incidents themselves, of the cumulative incidents. This is the cumulative incidence of event 1 plus the cumulative incidence of the event 2 is always the cumulative incidence of the composite. And this describes that, and that describes this. The other one is to treat this problem as a mixture problem, where pi is the proportion of people who will ever develop event 1. Of course, 1 minus pi is the complement, the other one. And this is when these people develop the event, and this is when these people develop that event. Now, the good news is that approaches 1 and 2 can be done with available software. This mixture, on the other hand, requires customized software. Okay? Now, how do we compare these things? If you use relative subhazards, you just make the ratio. Exposed, unexposed. Exposed, unexposed. And these are the ratios of the cause-specific hazards. And what is proportionality? Proportionality is assumed that these entities do not depend on time, are constant. There is a number every time. And so that this number is little a1, a number, and this is little bi for all the times. And what we show in this chapter is that of these 4 entities, mathematically, not empirically, but mathematically, only 2 can be constant. It is impossible, it is inadmissible that any 3 be constant at the same time, or that the 4 are constant at the same time. Only 2 can be proportional at the same time. And that's the bad news. The good news is that any pair can be. It's not like certain pairs cannot be. Okay? You know, these 2 could be the lucky ones to be constant. Or these 2 could be the lucky ones to be constant. or these two would be the lucky ones to belong. Okay? Furthermore, there is tethering. And there is tethering. Remember the ball, the tethering ball in high school, in middle school?
Yes.
Huh? Same thing here. Huh? It's a little bit of tethering. And it's not rare that it's tethering, because intrinsically these competing events are tethered. Huh? They're competing for us. Huh? Okay? And what is the tethering? If the two lucky ones are the two subhazard ratios, then they have to be on opposite sides of 1. One has to be above 1, and the other has to be less than 1. They can never be on the same side of 1. Okay? The other one is that if it happens that the lucky ones are the subhazards ratios and cause-specific hazard ratios of the same type, one of the two, let's say A1 and B1, they have to be equal. Okay? You don't believe me? You don't believe me? But we show that, let's go back to the case in which the two lucky ones are the two subhazard ratios. The subhazard ratio of ESRD is constant, and the subhazard ratio of transplant is constant. If that is the case, you could show this very easily that the cumulative incidence of the exposed group of each type is simply this expression of the cumulative incidence of the unexposed to the exponent of these two numbers. Okay? So you evaluate these two at infinity, and you could derive that A1 has to be this, where this is is among the exposed. Among the exposed, what proportion will have ESRD at the event? And this is the proportion in the unexposed of the event 1. And you could show that A2 is that. Well, it's very clear for any two numbers that if this number is greater than 1, that has to be less than 1. Okay? So, if that is the case, and this is what I get a lot of enemies, is that numerous papers have reported inadmissible constant relative hazards on the same side of 1. And this inadmissible result is simply really a diagnostic of the lack of proportionality. So when you read a paper and both of them are above 1, then you immediately could say, I'm sorry fellow, your hazards were not proportional. Okay? So that is and you don't believe me, but here are your peers. Here are your peers. Of this group reporting. And we observe all that have are in the same side of 1. All constant supervisory ratio are less than 1 is an inadmissible result. All this is an indication is lack of proportionality. And here are the data. All of the numbers less than 1. Okay? And what are the competing events? The competing events are type of AIDS. This is all different types of AIDS. And death without AIDS is the major competing event. Either I die without AIDS, or if I died of AIDS, of a given cause. And in all the causes. And Even though it's not 2, which is the case that I'm describing to you, but you cannot have all of them less than 1. And you could say, well, but no, don't be so mean. This is don't be so mean. This is 1. You look at that, 0.15. This is 1. So not all of them are less than 1. You cannot have either 1 equal to 1 and the other above 1. It has to be in opposite sides. Okay? So here it is, in the best families. Happens in the best families. Huh? Fine or fine and great. Huh? And in a very serious journal. Huh? And here you go. Minus 54. This is the fine and great. Fine and great for fine. Minus 54, the log of the hazard. This is the log of the subhazards. Minus 10. Another case of 1 and significantly less than 1. It cannot be. It cannot be. It happens in France too. Huh? It happens in France too. It's not like Europe is free of this problem. Huh? And here we go. The relative subhazard, subdistribution hazard. Huh? And yes, not significant. But this is well, but they are both in the wrong direction. Then here is a case where the yellow is 1323 and 136. It cannot be on the same side of 1. Significant and significant, both of them significantly higher than 1. Then here is a case where it's okay. You can see blue and red. Okay, huh? Because these are less than 1 and these are greater than 1. But this cannot be claimed on the proportionality. You cannot claim as a finding. This is expected. Okay? Scary. Huh? Here is a fellow who that there was 3 and had 2 problems. 1 on the same side of 1. All of them less than 1. Furthermore, he had some cases in which the person died, but it was impossible to determine whether the cause of death was AIDS or non-AIDS. And that happens to all of us. That happens in all the studies. But that unknown should not be treated as a third. It's really one or the other. It reminds me of the 1970s approach of treating missing data. Remember? That either I put the missing data as another covariate, and then I'm okay with it. That's awful to do that. Huh? Same thing here. Same story here. Huh? And Ronald is a good friend, but that's even among friends, you have to be honest. Okay.
You might lose friends this way.
My friends, so I've lost many. But that's the attraction of, that's the only few benefits of getting old. You know, it's over. You know, it's over. It's over. You don't have many years to suffer. So it's all right. to get in trouble. It's when you're young that you have to be careful. So here is again another case that is okay. 179 and 49, that's what you want. And that's not what you want. And interesting enough, these stars are great. This star says significant departure of proportionality reported. Beautiful. Beautiful. Stars mean okay. And that is and then there's no star here. In other words, in that case, perhaps proportionality was okay. Now, if you have on both sides of 1, it doesn't prove proportionality. I'm not saying that, but it says that under proportionality, that's the expected result. Okay? Okay. We fought with them. Now let's fight with the next ones. Let's do the next fight. The next fight is those that says, I don't know what to report, but I'm going to report both, so that I don't get in trouble. I want to report both. I do analysis with hazard, I do analysis with cause-specific hazard. I report both. Okay? Well, but typically you report them under proportionality. And the sad part is that you can prove that given under this, you can prove that actually the two numbers have to be equal. And you know how? It can be proved. You don't need mathematics really, because remember the definition: rate of change, cause specific 1 minus 1 minus cumulative incidence. Cause specific rate of change 1 minus 2. Okay. Well, at time 0, both of them are equal. The denominator is 1, and the numerator is equal. Okay? Got it? So, in any case, at 0, the ratio of the subhazard functions and the cause-specific hazard functions are equal. So if they are constant, they have to be equal all the time. I was equal to you at 0. And we are constant. They have to be equal all the time. That's the proof. That's the proof without mathematics. That if you assume they're constant, they have to be equal. Okay? And these people wrote a paper saying you should report both. You should report both. And computer analysis we saw so that well, but under proportionality I don't need to, because they're equal. So when you report different hazard ratios, again this is a diagnostic of that proportionality. And and if you report similar hazard under proportionality, it's not a finding, it's not confirming anything, it's expected. It's not like I have more evidence that this is the case. It's expected. That you see the title now of the lecture. It's not that I wanted to use a fancy word with an accent. It was that it is perilousness. So here are examples. Look at that. We did both and they're similar. Expected. Yeah? And here it is, different. I did cause specific, I did distribution, they're different. And so it's this lack of proportionality. Here you go. But here is a case where things behave. 1377, 136. That's what you want. But it's not a finding, it's expected. And you want this also. You want 268, 265, 1023, 996, same numbers. So that is okay. Same fellow, and here is a case where you have 146. You have 146 minus 50, 362, 134. Different, and they said, by the way, we also know that the partial proportionality. That is exactly a corroboration of the diagnostic. Beautiful. And here is a paper that was published in 2014, and in all these cases, you have different 138 different than 454, 154 different by 578, all different on their proportionality, all indicatives of lack of proportionality. Okay, now what about these other two? But this is really of curiosity, because nobody assumes that the subhazard of one is constant and the cosmplication of the other is constant. Huh? But this is very common, that both subhazards, and this is good because there are no restrictions on B1 and B2. That's what is so popular. Because if you deal with cause-specific hazards, huh, then you don't have the tethering that you have in the others. Okay? And that is very popular. Then we prove in the chapter that if you take 3, you get to an impossible result. Just to prove that 3 cannot be. So if you assume that the 2 cause-specific hazards are proportional and the subhazard of the event of interest is proportional, then you get to a contradiction. Okay? You get if you assume that, then this has to be equal to that. But that's impossible. This is always greater than that. And that's what it is there. And here is an example of a JAMA paper in 2011 in which they presented the 2 cause-specific hazards for death and for end-stage renal disease, and then also the subhazards for the event of interest, end-stage renal disease. Okay? So this is the and they reported 1, 5, 1, and 1. Okay? Then the fact that these 2 are equal is good, because that's what is expected on the proportionality. Okay? But if by both of them being equal to 1 implies that the 2 cumulative incidents of the exposed group are equal to those of the unexposed group. In other words, that you have the null result. If you have the null result, then this one cannot be significantly greater than 1. And that is the inconsistency. Okay? And what's indicative here again is that these relative hazards are not constant. Okay, then the 4 impossible, the 4 is even worse, and there are papers that publish the 4 constant, and that cannot happen. So, that's the conclusion. And most 2 can be, and please allow the hazards to be non-proportional. If you don't want to get in trouble and you want to assume proportionality, then use these 2. Okay? But if you want to be informative instead of avoiding trouble, you want to be better than avoiding trouble, then allow the hazard ratios to depend on time. That is the primary message of this. And yes, it is more complicated to communicate to the world relative hazards that depend on time, because one number is not enough. You need a curve. You need a graph with confidence interval or something like that. But, who told you that life was easy? Life is not easy, huh? Period. Huh? And epidemiology is even more difficult than that. Okay? So that is the primary message that I had is a quarter to
20.
Yep.
20 to 1, a quarter to 2, 20 to 2, we could stop here. We could chat about the mountains. And you could tell me where to go hiking. Huh? Or you could ask questions. Or I could keep talking. What are the two competing risks? What do you want to do? Questions? No? Protests? Yeah.
I have a question. So you mentioned at the beginning of your talk 3 approaches for dealing with competing risks, and the last one you said uses it's a mixture approach using maximum likelihood. Can you talk a little bit more about that approach, because I'm not familiar?
Okay, I'd love to. So what you do is, you're absolutely right. You have this mixture, pi, and which has a clear meaning. Proportion of people that develop event 1. And they come 1 minus pi for 2 events. And then the pi people, those who develop event, happen at a certain time. And then you need a distribution function to model those times. And then you need another distribution function to model the other times. And they better be separate, because the 2 events may not have the same timing. It's not like I could assume the same, okay? So the full parametric approach is to assume, for example, that, ESRD is a Y-ball with certain parameters. Transplant is another Y-ball. And then you estimate pi parameters. Pi, the scale and location of the Y-ball for one type, location and scale of the Y-ball of the other type. But if you have that, then you describe the full process. Not simply via hazards. Because the hazard is the soup that we have come up with. This measure is a measure. But it's a measure that has the attraction of replicating the cumulative incidence, but it still is a summary measure. With this mixture, you have everything. You could estimate hazard, subhazard, you could estimate cause-specific hazard, and more importantly, you could test whether the pi is different. For example, does the exposure modify the overall proportion? And you could also estimate how the timing is extended or contracted by a given exposure among those that have certainty. Okay? And since you ask, I'm going to continue. Because this is an analysis that we published in Epidemiology in 2010. And this is a very important study. The initial study was published in the New England Journal of Medicine in 2000. And we reanalyzed the data with this mixture approach. Okay? And it's a 1,000 clinical trial, 1,000, from 97 to this strategy, 503 to that strategy. Okay? And the idea was, on people in intensive care unit, maybe we should be careful in not giving them a lot of fluid. Maybe less fluid is a little better than a lot of fluid. And people were scared to do that because, no, we're going to give a lot of fluid, this person is in trouble. Hey, but maybe not, maybe measure it. So, clinical trial to test. Competing events, whether we achieve a good event, meaning you get out of the ventilator, and you start breathing by yourself, or this is the bad event. You die in the hospital. That's the mixture. That's the mixture. See that? The mixture, elementary probability. This is 101. Conditional probabilities. And we did a little bit than a Y-ball, a generalized gamma, a Ritzel model. And when we did this, we obtained these inferences. The pi, the percent of people in each of the 2 arms that reach unassisted breathing was 66 and 72%. Not significantly different. But what conservative did is reduce the time in the ventilator, 2.5 days, which is being in a ventilator is no fun, huh? If you could reduce that 2.5 days significantly, thank you very much, conservative, okay? And it didn't modify when the people who died did so. So this is a very specific inference. What conservative fluid does is doesn't unfortunately increase the number of people that reach assisted breathing, but make those who reach it in a shorter time. So what's the inference? Is this graph. That is the same, but the people who are the conservative have shorter time to it. Okay? In this case, this is a good event. A better accumulation is better. A higher incidence is better. To be able to breathe by myself. Okay? Very specific. So we went to, so you could see the mixture, how the mixture shine, and give a specific. Then we went to the subhazards and the cause-specific hazards. Said subhazards, how do you describe this process? Cause-specific hazards, how do you describe this process? And we allow for type dependency, being congruent with the fact that we didn't, and that is the result. That is cause-specific hazards of unassisted, the relative hazard of the relative cause-specific subhazards. Cause-specific subhazards. This is from the mixture model. That's from the semi-parametric approach. No, semi-parametric approach. Congruent, which is good. So both of them are agreed. Okay? So both of them agree, this is right, this is correct, we don't have any inadmissibility, blah, 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 blah. We respect all the... And the interpretation of this is, and it is correct, blah, blah, the interpretation of this is a little murky. It's not incorrect, it's not, this is it, but it's a little murky because it sort of indicates in a quick way that after 15 days, then the conservative is not good anymore. Okay? But here, a higher hazard is good. A hazard for a good event is good. Okay? But it says here that it crosses 1. That is because when you go to these cumulative incidents and you get to 15, then this curve already has reached its maximum and it doesn't increase a lot. But this one is still increasing. Okay? But this difference stays. That is the problem of the hazards. And that's what Miguel Hernán is so smart. The hazard of hazard ratios. It's a paper that he published in 2010. And it is alluding to this problem. That is intrinsic to the measure. Okay? And these are these are my friends. We belong to the same political party. We send our contribution to the same party. Okay? And it is not the one that's in the government now. Sorry. Anyway, so that is the mixture.
You say that there is no software available for using?
No. But I mean, we could make it. I mean, we have software, and it will become soon a command in Stata. But we're working on it. With Osama bin Laden.
Oh,
You remember Usama?
Oh, yeah.
Yeah. With Usama and Perilousness, whose email address is intelligent Perry at gmail.com. Okay, gente. Huh?
Any more questions? Still have 5 minutes.
Could you use Bayesian software to implement the mixture approach?
No, me.
already?
No, me.
No, wouldn't work.
Really?
You're saying it would not work? or-
I don't know.
Okay.
I don't know.
Yeah. Well, you try. Okay.
Yeah.
I've done a lot of mixture work in
Is that right?
Bayesian, but not in a survival.
Not in this context.
Not
I
in
see.
that context, so yeah, it'll help him.
I see.
Just a thought.
But Professor, we observe pies. Pies is not. We don't have to. We don't have to make a prior for this. I mean, we observe the pies. We observe the proportion of people who died of a certain event. This is observable.
So it's not really clustering. It's not, you're not assigning people to groups with probability. You know the group.
Oye, maestro, yeah, when I died of ESRD, count me on there.
Right.
And if I get transplanted, you count me there. So it's counting.
So then it's easier.
Yeah, much easier. That's what I do it. Yeah. Well, go hiding there, huh?
Thanks very much.
Okay, very good.